Okay, here we're going to talk about the linear transformation that's given to us by a matrix. So the idea is if A is an n by n matrix, then the function we get by taking t of v is equal to A times v is a linear transformation. And it goes from Rn to Rm. So notice this gets sort of reversed from the order up there. So let's look at this example down here. The matrix A defines a linear transformation t of x equals A times x. Well, what's the domain and codomain here? Well, if we look at this matrix, this is a 2 rows by 3 columns. So I guess I could, from the memorization thing, I could say this maps R3 to R2. But I don't like relying on memorization. Well, let's write this out. T of x equals AX. So you've got AX equals T of x. Or if you wanted to, you could call this a y vector if you wanted. Well, let's write this out. So A is 1, 0, 1, 4, negative 1, 1 times something equals something. All right, let's look at this. A is it's a 2 by 3, and we're multiplying it by a column vector. So this has to be one column. And how many rows is it? Well, to be compatible multiplication-wise with this, it's got to be 3. And what are we going to get out of this? We're going to get a 2 by 1. So we can see that our input here is from R3, and our output is going to be from R2. So you can write all that out and work it out. And honestly, I'd probably recommend doing that because it's not like I'm going to give you a ton of these to answer. And it's good to check what's going on. So this matrix defines a linear transformation. What's its domain and codomain? Well, again, you've got, let's see, you got this. What is this? It's 4 rows by 2 columns, which means you multiply it by a 2 by 1, and that gives you a 4 by 1. So it maps R2, should have made those blanks bigger, R2 to R4. Like that. All right. Let's do some multiplication here. Here's a fun fact. If L is a line in the plane and T maps R2 to R2 is a linear transformation defined by T of x equals AX, where the determinant of A is non-zero, then the image of the line is also a line in the plane. So let's use that to apply this matrix here to this triangle in the plane. Now that triangle, it has 3 points, and what the fact above says is that really all we have to do is apply this linear transformation to each point, and then we can just connect those points with lines. All right, so I'm going to take this 1, negative 1, 0, 2, and we've got 3 points over here. The first one's 0, 0. That one's really easy. You multiply it out, you get 0, 0. So this point gets mapped onto itself. All right, the next point, let's see, this point here is at 2, 1. So if you multiply it out, let's see, you get that times that, so that gives us 2 minus 1 is 1. And then if we do this times this, it gives us 2. So this gets mapped to the point 1, 2. That's this point up here. And we can just connect these with a line. All right, now what about this other point? The third point is 1, 3. And if we multiply this here, let's see, you get the 1 minus 3 is -2, and you get 6. So -2, 6. I didn't make my grid big enough. So -2, 6 is going to be up here. So that's the image of this triangle under this this linear transformation. Let's look at one more. It says find the image of this house under the linear transformation with this matrix. All right, I don't want to do all this multiplication by hand, so I'm going to use octave to do it. So let's see. The transformation we have here is 0.8, -0.6. I'm going to enter that in as a 2 by 2 matrix. I'm going to call it T. So we've got 0.8, -0.6, then 0.6, 0.8. All right. So now I'm going to take this and multiply it by, let's see, we've got 5 different points on the house. The first one is 0, 0. Well, let's, if I put that in, 0, 0, it gives me 0, 0. So let's see, I guess I'll draw these in green. So this point gets mapped to itself. And let's do these in I guess counterclockwise order. The point, this is 2, 0. If I multiply this by 2, 0, it gives me 1.6, 1.2. And let me show you something. What we can do, we can't put all of these in as one big vector or one big matrix. Let me show you what I mean. The points that we have in the original graph, we've got 0, 0, then we've got 2, 1. I'm sorry, 2, 0. Then this one's going to be 2, 2. The house top is 1, 3. That looks like a -1. 1, 3. And then the last one is 0, 2. So what we can do is take all of these and multiply them all at once. So I'm going to take this and I'm going to multiply it by this matrix. 0.8, -0.6, 0.6, 0.8. Let's just go through and have octave do all of that for us at once. So I've already got T in there. Now let's look at our matrix. We've got 0, 2, 2, 1, 0, 0, 0, 2, 3, 2. All right, when I multiply that out, I get this. 1, 2, 3, 4, 5. Okay, they're all on screen. So if I start plotting these, I've got 0, 0. The next up is 1.6, 1.2. So that's here-ish. And then 0.4, 2.8. So 0.4, 2.8 is going to be about there. Then -1, 3. And then -1.2, -1.6. All right, so those are the 4 points on the house. And if I connect them together, remember I did them in counterclockwise order. So if I wanted to connect these together, I'd get this. Let me make this a little bigger. I get this, 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 this. And we've also got the line here. So if you notice what this did, this rotated the house counterclockwise a little bit. Um, I'm gonna copy those down. We got 0, 0, 1.6, 1.2, 0.4, 2.8, negative 1, 3, negative 1.2, 1.6. If you think about it, it took this house and rotated it. This is sort of the very beginnings of how computer graphics do certain things. Rotating things around or reflecting them. But anyway, that's the green image there is the image of the house under this transformation. You might say, what's that angle? Let's see, the angle there is... I actually need to look this up because I forget sometimes which one is sine and which one is cosine. But I'm going to look in the textbook here. This is an example of a rotation. Yeah, this is a rotation matrix. And the way those work is you have cosine theta here and here. And then you have sine theta here, negative, and sine theta here, positive. So on this example, we used the angle that has a sine or a cosine of 0.8. Let me grab my calculator. If I take the arc cosine of 0.8, it gives me this value here. So that's the angle that we rotated this thing by, 36.8 something degrees. .869, yada yada yada. I picked it because 0.6 and 0.8 are nice numbers. But if you wanted to find a matrix that would rotate the plane, say 10 degrees, you just take 10 and plug it in for theta here, and that would give you the rotation matrix. We're going to talk more about that later. That's section, I want to say it's 6.3, talks about computer graphics and other applications. And so we'll talk about this stuff more later. Right now, it's just kind of a teaser for, this is the, one thing you can do with linear transformation. All right.